Hello everyone and welcome back to Intelligent Machines. I'm Dr. Mohan Das, a PhD in Machine Learning and Artificial Intelligence. And today's topic is something really exciting, especially if you're looking for a practical and impactful computer vision project. Today we are going to explore how re-identify animals in the wild using computer vision. This is a widely studied problem, particularly useful for tracking endangered species for monitoring wildlife. Traditionally, scientists used physical tags on the animals which you can see here. For example, there is a bird here, there's a seal here, a rhino here to identify them. But this required capturing the animal, sedating it, and then attaching a tag, which is not only labor intensive but also risky for both animal and the human. So, what if we could do this just using images and AI? Well, now we can. The idea of re-identification. Let's say you have a bunch of images of known tigers. Tiger 1, Tiger 2, Tiger 3. These are the images of tiger that you already know that exist in the wild and you have been keeping track of them. Now, there is a camera trap that you have put in the wild and it captures new images. Our job is to find out is this new tiger that has been captured by the camera, does it already known to us? If yes, then which one is it? And if it is not known to us or it does not belong to any of the already captured tiger images that we have, then we should add a new ID to it, let's say call it Tiger 4 or Tiger 5, and add that back to our database. This is the core of image based re-identification. So now comes how do we match two images? There are classical approaches like Shift, ORB, and so on. But in this video, we are going to talk about a deep learning based matcher, which is called LightGlue. It is by far the state of the art, along with a feature extractor called SuperPoint. The idea is rather simple. You take a reference image, which is of a known tiger, and compare it to a new image, which has been captured by the camera. It can be an image or it can be a frame of the video, and then compare between these two. And once you compare, you get something like this. If there is a match, then it shows that which point in your reference image are matching with the current image. So this green dots that you see, it's matching that which point here is matched to which point. And here we say that if the number of matches is greater than a number of threshold, in this case, let's say 20. If we get more than 20 matches, we call it, okay, we find a positive match. And this image already exists in our database. And which image is it? This reference image, whatever class, whatever tiger number we have given to this reference image. We do this with all the reference image that we have in our database. But of course, as nature is messy, sometimes the model matches grass instead of focusing on the real object, in this case, the tiger. For such cases, we use a simple unit to remove the background and focus on the animal itself. And here how the whole pipeline for the light glue works. They have made available this model as a repository. This is the whole repository and they have given example codes and everything. You can install it by calling this. I have put this in the requirement.txt, so you don't have to do any problem. And these are all the new matching algorithm. And you see the light glue model, it is not only highest accuracy, it doesn't have only the highest accuracy, but it can process most amount of images per second as well. That means it has high throughput as well. So it is not only good on this axis but also good on this axis. That means it is lightweight and high accuracy compared to its competitor. So how does this work? The input are two images. This is the reference image and this is the current image. We extract features using SuperPoint. These are the extracted feature. This DA and DP are the extracted features, and PA and PV are the location of the key points, basically the X and Y. This feature there, and this is our light glue architecture. This particular part is our light glue architecture, and inside there are both cell attention and cross attention. That means these points attend to themselves and to the key points of the reference image. And finally, after each layer, so this is layer one and it goes up to layer n. Basically, this is repeated until 9 steps. And finally, we get a matchability score. That means each point in each image gets a similarity score with each point in the image B. And whichever has the highest will take that. Also, there is one step which is called pruning. That means after one every layer of this cross attention and everything, you find some points which have no matches or which have matches beyond below a threshold. Then you discard them because this point because if you have more number of points, you have to do more number of attention operation. So this thing becomes more computationally intensive. So that's why pruning is a better idea, that after each step you discard some of the key points that are not needed. So these are let's say we have image 0 and image 1, and this is the corresponding code for that this device decides whether we have a GPU or CPU. It also works fairly well on CPU in my opinion. Then this is the extractor or the SuperPoint extractor, which helps us extract a feature from the images. And this is the matcher, which is the LightGlue matcher that takes the extracted feature and matches them. We're using SuperPoint. And this filter threshold 0.5 helps us prune the key points after each layer. And there are total nine number of layers. But we after a certain point, if there is no images left to be pruned, we stop them. We first use our images in the SuperPoint extractor to get feature 0, and for both the images we do the same, and then we pass both this extracted feature to the matcher or the light group, and finally we get the matches. Now let me show you a practical demo. I used a National Geographic tiger video as my test input. This is the the video. I imagine that this has been taken from a camera that I have put in the wild, and I have some images in my database that I would like to match with this. There are multiple tigers at some frames also, and there are different views of the tiger as well. You see. So now let me show you the result after I have run the matching algorithm. So this is my reference image that I am going to match with. This is I just screenshot from one frame. So here you see the red points are the ones. So here this red point is matched to one of the red points of these three. So there are one, two, three. These three red points are in matched with one, two, three. Three red points here. These are definitely false matches. It's matching somewhere here with somewhere here. But we'll see. And because there are like we also decide based on the number, so if there are less than 20 matches, we don't consider this as a match. So here you see we get a lot of matches right now, and they are more or less like some are with the ground and the grass, but for example look at this point. This point is probably matched with the one here. Now some point here, so we don't know which tiger it has been matched with. But yeah, this is my very interesting that you see now two tigers are in the frame, and but now you see it perfectly matches with this one. And now see two tigers are in frame, two tiger faces are in frame, but the model matches with this tiger faces more and not at all with this tiger face. If you personally ask me, I would know which tiger this one belongs to. Of course, this is not the tiger probably, so it doesn't matches. And also one disadvantage here is we just took an image from one side image, so probably from the other side this might be from the right hand side. If you have taken the image right side view, then probably it would have matched because they have this stripes in different. It could be different from left to right. That I took this screenshot from around this time. So this is exactly the tiger that we. These are the same tiger basically because I took one screenshot from here. So you see the left hand part is matched exactly here. And now this is the screenshot I took, so it's matches basically 100%. But one good part is here we don't need any training. This all are in the inference space, inference time. So this tiger is definitely not our tiger because it's not matching at all. any no key point. This is our tiger probably. It's not matching with this one. And now you see most of the matches start happening here. With this, I like exactly the same matches here. That means okay, this is our tiger, not this one. It is indeed very cool. That was the whole demo part. Now I'll go into the coding part. I won't make it very lengthy. The most important part is this LightGlue library, which you have to use. I have given the link to the GitHub repo, or I have given this requirement.txt. You can directly install from here as well. All right, and this YTDLP, it helps you download YouTube videos directly. Probably you won't need it. If it's optional to you. This is the link of the video. This is when I am. This is how I import the extractor and the matcher, and this is the for these two images. I have taken two screenshot A1, A2, and they are the same. They're the same cat, sorry, same tiger. These two are the same tiger. So I want to see if it matches or not. So it very well matches, especially the face part. And how does it work? So first we load the images, and now this image 0 and image 1 are in PyTorch format. Then we pass it to the extractor. Extractor is also a PyTorch model. Matcher is also a PyTorch model. Using the extractor, we extract the feature 0, feature 1, and then in the matcher we pass both the features. And now we get the matches. And we use these matches to then plot this. This Viz 2D plot is given by this LightGlue library itself. So you can do some nice visualization. But I'll write my own code when I run this on the video, because if you use this load image, you have to pass the path of the image. But I don't want to do that. I don't want to save the image as a PNG or something and then read from there. I'd rather do it on the fly. That means I want to use the numpy array of the frame directly to pass into my extractor and then match. So for that, I created this function, match video frame. Most of this part are same. Like from this part is exactly same as before until this part. The only change is here. That means I'm passing in a numpy array instead of PyTorch tensor, and then this two tensor function that I create, it converts the numpy array into a PyTorch tensor. That's it, as simple as that. And here I'm doing using OpenCV. I'm plotting the matched key point as red dots that you saw in the video. And after that, I'm running this particular, what do you say, the function frame by frame. So this is my video, this Tiger MP4 video. I'm creating a cap to capture it. And here are some values that the FPS, the width and height. I'm manually setting this width and height. And then I'm creating another out variable which writes and then in a loop, I'm basically writing the video. So here, I think here you get this is my frame. Then this is the function match video frame. We get the matched, and then I use this matched visualization to out.write match, and that's how it writes that and creates the video we saw. That was all about this, and I hope you find it interesting. It could be a very nice computer vision project. Yeah, so that was it about this video. Check out my channel for other computer vision related videos, and I have also shared my TopMate and Upwork profile if you are willing to take a consultancy. So till the next time, stay curious.